Hello everyone, welcome back to my channel. Today's lecture is about halogen derivatives. This in this topic we will discuss about few stuffs, for example, your who are halogen alkanes, what are their physical properties, and then the type of chemical reactions they undergo, the mechanism part. I mean, that's the most important part over there. And then you have your SN1 mechanism, SN2 mechanism, and the types of reactions. That's it. If you break down the entire topic, it's going to be very simple. Now, who are halogen alkanes? We all know who are alkanes. Alkanes are chemical who have like carbon to carbon single bond. And halogen alkanes are basically the same thing, but instead of having one of the hydrogen being replaced by a halogen group. For example, this hydrogen has been replaced by a halogen group. In this case, it could be your, let's say, Cl or bromide or something else. Now, when you have a carbon that has an halogen attached with it and it forms a covalent bond, you know they're sharing electron right in between. Now, chlorine is a little bit more electronegative compared to that of carbon. As it's more electronegative, it's going to pull the electron towards itself slightly, making it del negative and making this one del positive. Now, one side of this carbon has an alkyl radical, and the nature of alkyl radical is such that it's going to push an electron towards a central carbon atom, making the positive charge decrease a little bit, as in it spreads out less on the bond a little bit. All right. Now, what happens when you have like one alkyl radical? If you have one alkyl radical and it pushes an electron towards a central carbon atom, reducing the positive charge density, we say this kind of setup or this kind of halogen alkane, primary halogen alkane. Primary halogen alkane. If you have, for instance, primary halogen alkane, it can also be sometimes called as 1-degree halogen alkane, all right? Now, if you have two hydrogen atoms being replaced, for instance, you had like two methyl chloroethane, for in this case, you have a carbon with a halogen. Again, del negative, del positive happens due to electronegativity differences. And then you have two alkyl radical. When you have two alkyl radical, they push two electrons towards the central carbon atom. Positive charge decreases all over again, and making it secondary halogen alkane. Sometimes we do call it second degree. Now, when you have, for instance, a carbon with on the three sides of it, you have like alkyl radical. What happens is, as you guys know, that chlorine pulls away the electron towards itself, and carbon has like del negative, del positive, and from the three corners, it gets electron towards the central carbon atom. As the electrons are donated from the central carbon atom, what happens is the positive charge decreases, and the chlorine gets to leave the structure easily, making this one totally positive as chlorine undergoes a fission reaction. In this case, it's going to be heterolytic fission, all right? Now, we call this kind of carbon tertiary halogen alkane, or sometimes third degree. All right. Now, in terms of stability, one of the most stable carbocation formed are the tertiary halogen alkanes. That's because since they have like three alkyl radical from pushing electrons from three corner due to positive inductive effect, this carbon gets to spread out most of its charge around itself, making it positive. However, the most least stable is the primary halogen alkane due to the presence of only one single alkyl radical. Now, let's move into their physical properties. Whenever we talk about the physical properties, we usually emphasize on solubility and their boiling point. So about their physical property, what do you mean by physical properties? Well, usually when we talk about physical property, we talk about boiling point. Boiling point is something that completely depends on intermolecular force of attraction. Let me write the full form of it. Intermolecular forces. Now, if you guys have studied the chapter of bonding, covalent bonding and ionic bonding, you'd know intermolecular force of attraction pretty details. Now, there are like two classification of intermolecular forces. One is van der Waals, and the other one is your hydrogen bonding. Now, we all know that when it comes to van der Waals, there are like branches of having permanent dipole and induced or temporary dipoles. So as the electron number increases, van der Waals forces increases. If your chemical is like nonpolar and has like a long chain, of course you have to remember that induced dipole and temporary dipoles are being set up. If your chemical is like polar, pretty polar, and has electronegative difference between them, that is undergoing both of these, and almost all ammonia of it will undergo permanent dipole. However, if any of your covalent compound consists of nitrogen, oxygen, or fluorine, and then they have hydrogen among themselves in the other part, that means their compounds will be able to do hydrogen bonding. I usually say that enough particles undergo hydrogen bonding. Nitrogen, oxygen, fluorine combined with hydrogen in their bonds. Now, when they do hydrogen bonding, why do we call these forces and why do we call this bonding? Bonding usually is a term that's described when electrons are involved in any kind of interaction. That's how covalent bond, ionic bond name came up. Now, why is hydrogen bonding a part of intermolecular force of attraction? Because it happens when the bonds are formed and when one compound's hydrogen is trying to interact with another compound's lone pair. For instance, you have like ammonia, right? You have ammonia and you have another ammonia. You have another ammonia right here. So what happens is the hydrogen from one ammonia will interact with a lone pair of the electron of nitrogen. And this hydrogen will interact with this lone pairs of the nitrogen. Since it's interacting with the electron, not like something else, that's why we say it's hydrogen bonding. And it usually happens between nitrogen, oxygen, fluorine because they have the most availability of lone pair when it comes to interacting with hydrogen among themselves inside the compound. Now, what happens with your this was a brief explanation about your intermolecular force of attraction. But what happens when we are talking about halogenoalkanes? Let me emphasize a little bit. So when we talk about halogenoalkanes, we have like a chlorine group here, and we have a carbon here, which is del negative and del positive. Of course, this chemical is slightly polar. When my chemical is slightly polar, this part could be the polar region. This part, exactly, carbon to chlorine part is the polar region. However, this part, the alkyl radical part, is nonpolar. So if you have like nonpolar edges, what will you get? You will be able to get induced or temporary dipole. That's going to be set up. However, due to their polarity, they'll also have their permanent dipole being set up. As their permanent dipoles are set up and more induced and temporary dipoles are being set up, what is happening is it's going to have a very strong intermolecular force of attraction. And as it's going to have a very strong intermolecular force of attraction, other than alkane and alkene, halogen alkenes will have a really high boiling point. As intermolecular force of interaction increases, what happens is energy required to break the bond, energy required to break the bond increases, hence boiling point increases. Primary halogen alkenes usually have like higher boiling point compared to secondary and tertiary halogen alkenes of the same molecular weight. That's one of the causes, honestly. This is because of the surface area of the primary halogen alkane is higher. As in, primary halogen alkanes are more like spread out. They're like not branched. However, when you have like branched hydrocarbon and halogen alkane of same molecular weight, what happens is, for example, the MRs are same. However, one is branched. For instance, I have like CH3, CH3, HCl, and the other one is like CH3, CH3, all right, CH3, CH2, CH2Cl. This is like straight chain, one go, And this is like a little bit branched chain, right? Because the branching happened here. As it's branched, this exposes less surface area. However, this one has like a more this has like a smaller surface area, and the other one, the one that is not branched, that's like a straight chain, has a higher surface area. So what happens is the one that has like a higher surface area usually happens to be the primary halogen alkane. How is that so? Because this guy, the carbon who's connected to the Cl, has two hydrogen on both corner and a longer chain of, like, let's say, alkyl radical on the other corner, which makes it have a higher boiling point all over again. So remember that the boiling point does not only depend on the polarity and non-polarity. Of course, this is one of the most significant part, but it also depends on how your alkenes are or halogen alkenes are arranged. If it's primary, then one side will be elongated and it's going to be a straight chain. This is more surface area, more contact point, more boiling point. If it's like a tertiary alcohol, it's less boiling point because the mass or the force is distributed due to electrons motion. Now, whether they're soluble in water or not, well, as you guys can see, they're polar and non-polar. They have both the regions there available. They are 100% very much soluble in organic solvent. However, they're insoluble in water. Why are they insoluble in water, even though they're like polar? In order for it to be soluble in water, the main criteria has to be fulfilled. And that fulfillment is basically your hydrogen bonding. Does your halogen contain any of these particles, N, O, and F? If it doesn't, it's not going to interact with water. It's not going to form hydrogen bonding. It's not going to be soluble in water. Simple as that. So solubility with organic solvents do occur. However, solubility with water cannot be happening because no hydrogen bonding available. All right. Now let's move to reaction mechanism. So in the beginning of the lecture, I did talk to you guys about something very important, and that was primary, secondary, tertiary halogen alkanes and their carbocations. Now, when you have like mechanism to be followed, here we have like two mechanism. One is SN2 mechanism, the other one is like SN1 mechanism. What does S represent? S here represents substitution. What does N represent? Nucleophilic. Okay, now why is it called nucleophilic? Here, species called nucleophiles attached to the carbon atom. Nucleophiles themselves are negative and they approach to a positive zone. And here, 2 represents reagents involved in the slowest step. So, when a reaction happens, it happens in multiple steps. So there's a step where the step is pretty slow and the reaction is about to happen. It's gathering all its activation energy and proper contact point to react with it. The slowest point is usually the reaction or the point where we get to, decide what the rate will be of the equation. Now, here, 2 represents the reagents involved in the slowest step. Here, 1 represents the same thing as well. Now, who does SN2 and who does SN1? SN2 is usually done by your tertiary. Sorry, my bad. Primary halogen alkane. And SN1 is usually done by your tertiary halogen alkane. Now, when it comes to primary halogen alkane, why does it do SN2 mechanism? Let me explain you. So what happens is, for example, you have like in this case, I'll probably draw here bromine, and then I'll draw here like 2 bromo, oh no, sorry, my bad, 1 bromo ethane. I'll draw this chemical. Who is more electronegative? Br is. It's going to take away the electron towards itself. Del negative, this is del positive. Now, initially, what happens is the carbon-bromine bond is polarized due to the electronegative difference between your bromide and the carbon atom, because this is like a larger nucleus, this is a smaller nucleus. This gets to pull the electron towards itself, making it negative, making it positive. Now, there's a nucleophile. Nucleophiles are basically negative species. It can be any nucleophile. It can be NaOH. So if you're reacting, let's say NaOH in aqueous, Na is positive, OH is minus. So let me erase everything else other than the minus chemical. So here in this process, OH is added and OH is acting as a nucleophile. So the nucleophile is attracted towards a slightly positive carbon atom. So as it's like interacting right here with its lone pair towards it, what happens is the as you can see, the central carbon atom has an alkyl radical, but sadly, the alkyl radical is only one present in here. So they're going to push the electron towards the central carbon atom, but it's not enough to cause bromine to leave. Bromine is like a pretty strong element when it comes to attachment. However, it's not completely attached because it's electronegative and it's going to take away the electron towards itself. But it's not being able to break the bond because this effect is not significant. What happens is when a nucleophile comes in, this bond breaks down immediately. However, in order for this bond to break down, a nucleophile has to come in. So when the bromine is leaving, another nucleophile has to join in order for that chemical to, let go of bromine. So, or bromide. So what happens is there's a point in the reaction where we have like 5 groups attached. It looks like they're attached, but however, bromine is leaving and your nucleophile is coming in. Now, what happens is this eventually we call this state transition state where the carbon atom is bonding is just about to break and another bond is supposed to be formed, and we have like 5 groups attached to it. The movement goes on until the nucleophile firmly attaches with the carbon and the bromine has been expelled as an Br minus ion. And the nucleophile has been substituted the bromine. Now, what happens is this is like the transition state, and this is like the slowest step. Now, the next part would be your chemical has been substituted. You have your OH, you have the alcohol, you have your Br being removed as bromide ion, okay? That's it. You need to understand another concept is that like the nucleophile here, I was hasting while I was doing it, so therefore I didn't draw it correctly right here. The nucleophile, whenever it's like joining in order to make the bromine leave, you need to note this entire thing that the nucleophile approaches the halogen alkane in the opposite side of the bromine. So let me rearrange the entire platform for you guys. So let's say, let me draw it completely in a different note. For instance, if you have like hydrogen here, a nucleophile will be attaching right, if the bromine is right here, the nucleophile will be attaching right from the opposite corner. It's crucial to get the orientation of the atoms right because the molecule has been inverted at the end of the reaction, and this inversion configuration is usually happen when the chemical that the reagent that's about to leave, the substrate that's about to leave due to the coming reagent which is about to attach. All right. Now, let's talk about SN1 mechanism. Well, SN1 mechanism happens for tertiary halogen alkane. Now, how does that work? For instance, you have like CH3, CH3, and then I can draw here a little bit of more carbon, CH3, and I have here my Br. Now, Br is electronegative, no doubt about that. This is still positive because of electron difference. Now, they both push electrons towards the central carbon atom. Now, what happens is, generally, the reaction happens in 2 stages. In the first stage, the small portion of halogen alkane ionizes to give a carbocation. Once the carbocation is formed, it will immediately react. Now, why does it form carbocation? Why can primary halogen alkane here form a carbocation? Because in order for carbocation to be formed, the bromine must leave the structure with two of its electron, as in like the one shared by carbon as well, and undergo heterolytic fission to move out. Now, it happens slowly because the alkyl radicals are pushing electron towards the central carbon atom. As the central carbon atom is being pushed, is being held in position and given electrons from three corners, the positive charge on top of the carbon drastically reduces the partial positive charge, which causes bromine to face a repulsive factor and leave the structure. But this doesn't happen immediately, it happens with time. And that's why this is like a slowest step. And as the bromide decided to leave the struck carbon atom with two of its electrons, taking it with it, it's no longer del positive, rather it becomes positive. Immediately, if you have like a nucleophile right there and then in there, what happens is the nucleophile comes in and readily attaches with the carbocation. For example, in this case, if you had like OH, it would come and form the alcohol. Now, tertiary halogen react through SN1 mechanism, that's for sure. That's what we learn. If primary halogen alkanes were to react in the same manner, the primary carbocation formed would be relatively unstable, resulting in high activation energy for the reaction. So energetically, tertiary carbocations are way more stable. However, primary halogen alkanes are way less stable because they'll require more activation energy. However, this requires less activation energy because the bromine leaves because the three alkyl radicals are enough to cause the attraction to cease away. All right. Now, let's look at the reaction chart of, since you have learned about the mechanism, now let's talk about the types of reaction available for halogens, because that's one of the most important part of organic chemistry. Now, the type of reaction halogen alkanes undergo are usually substitution with hydroxide, cyanide, ammonia, and then we have elimination. So for that, the first thing what I'm going to do is I'm going to write here a very small halogen alkane. For in this case, I'm going to write here CH3, CH2, Br. Oh, so I have here your bromoethane. Now, if you decide to react, let's say, bromoethane with NaOH, but you have decided to react it with NaOH in the form of aqueous solution, and you decided to give heat under reflux as well as a condition, what's going to happen is here the OH is going to act as a nucleophile and it's going to replace the bromide from the compound. So it's going to form CH3, CH2, your OH, and this Na will catch up with the bromine and form NaBr. This type of reaction is nucleophilic substitution. Okay? Now, the opposite usually happens with the same chemical, but if you apply a little bit of different reagent now this time. If you add like NaOH, however, you decide to add it not in aqueous, but in ethanolic solution. And you decided to do a little bit of your heat under reflux. This is no longer substitution, rather this is elimination. Why? I'm going to tell you. Because you see, when we are adding NaOH in ethanol or ethanolic solution, the OH here acts not like a nucleophile, but rather as a base and substitutes its position and it takes away the hydrogen from here. So it's acting as a base. So what does base do? Base love protons. So if it takes a hydrogen from here, if it takes a hydrogen from here, the Na will take the Br from here. And as they're taking away the important chemicals, they're breaking the bond down, they're taking the elements apart, they have like spare electrons. So the spare electrons arrange themselves to form an alkene molecule because you've removed two species from here. And the rest is NaBr and H2O as a byproduct. Here, you didn't get a byproduct as H2O. However, here you will get this. Now, the next reaction is with ammonia. If you ever decide to, let's say, react or substitute, let's say if you ever decide to substitute with ammonia, you have to make sure that you have applied here ethanol as well. And you have to give here a little bit of your, what's that called? You can't do here heat on reflux. You have to heat in sealed container. Now, when you do so, ammonia has like a lone pair, so it acts like a nucleophile. So it's going to attach to the position where the bromine is. So if it attaches with a position, now nitrogen can only do like 3 bonds. So it's going to get rid of one of the hydrogen and forms CH3, CH2, NH2. So what happens to the extra hydrogen that leaves the structure? That extra hydrogen catches another ammonia molecule in the ammonia solution in ethanol and forms ammonium plus ion. And that reacts with the Br to form ammonium bromide. So we have ethylamine and then we have our ammonium bromide. Because why? Because this ammonia got rid of one of its hydrogen, and that hydrogen got accepted by another ammonia to form ammonium that reacted with Br. Now this is our ethylamine. Now, the fourth reaction is a little different. The fourth reaction is with your cyanide. In this case, we will be applying here your potassium cyanide and in ethanol, and you have to do heat under reflux. In this case, we produce nitriles. How? For example, here the cyanide has like lone pair, the carbon has a lone pair that attaches itself and it acts like a nucleophile, it attaches itself with the position where the bromine is. So CH3, CH2, C triple bonded N. Now, how would you name this? This is basically propanitrile. Propanitrile. Now, nitriles are usually used when you have to see carefully that your initial chemical had like 2 carbon, but somehow the final chemical has like 3 carbon. That's 100% sure. You have to be 100% sure that one extra carbon was added by the nitrile. Now, when you form this nitrile, propanitrile, you can break it down clearly in a very, very easy way. You can break it down in the process called hydrolysis. And when you do so, you can add inorganic acid or inorganic base. If you add inorganic acid, it's going to form CH3, CH2, COOH, as in carboxylic acid, and your ammonium plus ion. However, when you add NaOH, this is the base, it's going to hydrolyze it and form carboxylate salt, and it's going to form ammonia gas, a very pungent smelling gas. So therefore, if I ever want to create acid, but I had like, your halogenalkane, I can use potassium cyanide and then hydrolyze it to get the acid. That's all. These are all the reactions you need to know from halogenalkanes. If you really liked my video and found it informative, please do comment down below and let me know how I can help you more. All right, guys, have a good day.